that's how you gotta set
Yeah.
up.
Good afternoon. Today we are going to start velocity analysis of mechanism. So we are done with displacement analysis. In displacement analysis, we learned when we are given with a mechanism, for example, like something like this 4-bar mechanism, we find the degree of freedom, which is 1. We would like to know when the input link is at the angle of theta 2. Find the location of other links, link 3 and link 4. Meaning finding the angle of theta 3 and theta 4. Theta 2 is given. A given value of theta 2, find theta 3 and theta 4. So a mechanical mechanism is a system which is moving. So meaning we can have velocity analysis. It means when this 4-bar mechanism, suppose this is a crank rocker mechanism. When this 4-bar mechanism, the input link is running at a speed. The speed can change over the time, or it can be a constant angular velocity. So in any case, we would like to know at given value of theta 2 and omega 2 is theta dot 2 or d theta 2 over d theta 2 over dt, how fast theta 2 is varying over the time at this given angle and angular velocity. What would be the angular velocity of link 3 and link 4? Theta dot 3 and theta dot 4. This is what I mean by velocity analysis. So for example, in this video, when we have this 4-bar mechanism which is running, this is a slider crank because this can complete 360. This is a crank. We would like to know, in this case you can see the crank is a rocker. The crank is running at a constant speed, but it can run at the varying speed. So when it's running at constant speed, for example, at this specific angle, what would be the angular velocity of this guy, which is represented by omega 4, and what would be the angular speed of this guy, which is represented by omega 2. So this is called velocity analysis. So we are going to do this in this chapter. So we are going to start working on analytical approach. There is graphical approach to the velocity analysis, but I used to cover the graphical approach, but I prefer to just cover analytical approach to velocity analysis. We are going to do this for offset slider crank, 4-bar mechanism, and inverted slider crank, the standard form of the mechanism that we have covered for displacement analysis. Then we go through the velocity analysis of any given mechanism. Once we learn about the approach, we can use the approach and the techniques to derive the velocity analysis, to do the velocity analysis for a given mechanism. So before we start with the first mechanism, let me just briefly talk about the velocity. Suppose we have this rigid body which is moving along x in this direction. If I ask you what would be the velocity of this rigid body, you can say how fast x is changing with time, or derivative of x with respect to time. It's going to give you the velocity of this rigid body. We can represent it with x dot as well. So x dot dx over dt, both are representing the velocity of this rigid body. We have angular velocity as well. Suppose this bar has the angle of theta with the horizontal line, and it's moving along this circle. So the angular velocity is defined as how fast theta is varying with time. I can represent that by omega or theta dot. So these are the notation that you are going to see in this course. Theta dot is the angular velocity. X dot is translation of velocity. Alright. Let's see. Suppose we have x and y axis, and point P is somewhere here. I connect point P to the origin. OP. This distance is r, so the distance of point P from the origin is called r. If I ask you, and this angle is theta, if I ask you what would be the x component of point P, the x component of point P, which is this distance, you can simply say that the r cosine of theta, and y component of point P, which is this guy, y of P, is r sine of theta. So y component and x component of P as a function of r and theta. Now, assuming that point P is moving in this direction along the time, it's moving along this path. So when it's moving along this path over the time, r is changing at the same time theta is changing. So r can change, theta also is changing. So I would like to see if y is r sine of theta, what would be the derivative of y with respect to theta? Find this for me. And how can we find derivative of y with respect to time? So first, think about this, if y equals to r sine of theta, and then use the chain rule to find derivative of y with respect to time. Is that clear? Yes. At the moment, I'm just asking for this. Just tell me what would be dy, how fast y, y is changing with respect to theta, and then how y is changing with respect to time.
I think 4 o'clock. I was like, I thought you were talking something else.
Yeah, and I asked you if you did it. And I think you walked away, but I can't remember. I was like, oh, okay.
I had so much in my brain. I was like, I didn't take it.
It's like, give me.
What can you do now?
Number 6. Number 36, journey. Okay, r cosine theta. What do you think about this? Okay. Yes.
So for the first one,
For the first one, it would be
within 3 as the theta terms.
this one.
Yeah.
For the first one, you have a function r and theta. You differentiate y with respect to theta. R is that a function of theta, so we differentiate sine of theta with respect to theta, which is going to be cosine of theta. That's correct. Second one, you don't see the term of time here. R and theta, they are not time. But we know that R is changing with respect to time. Theta is changing with respect to time. Because when time goes, R value is changing with respect to time. Theta also is varying over the time. So when you don't see the variable explicitly here, we are going to use the chain rule. dy over d theta times d theta over dt plus dy over dr times dr over dt. Chain rule. So R and theta, they are varying when time is changing. As you see, R distance is changing when it's moving. Also, the angle of theta is changing. But you don't see T directly here. You are going to use the chain rule. dy over d theta times d theta over dt plus dy over dr times dr over dt. Any question about this?
The second part go to zero.
All right, let's look at this. I'm looking for dy over dt. I will see how it's gonna change. I'm working on dy over dt. The first step, dy over d theta. The derivative of y with respect to theta. It's gonna be r cosine of theta. We differentiate this with respect to theta. Times d theta over dt. This term, it's gonna be the angular velocity of theta, which I represent by theta dot or omega. So theta dot, it's an angular velocity, plus dy with respect to derivative of y with respect to r. We have 1r, derivative of this with respect to r is going to be 1 times sine of theta times dr over dt. This distance, how this distance is varying with respect to time, the distance. It's r dot. So the y component of point P has this as a velocity of that. So it's gonna be y dot of point P. It's gonna be dy over dt, and it's gonna have these two terms. Any question about this? So x component would be r cosine of theta. X component of P is going to be r cosine of theta. So dx over dt would be x dot of point P. How fast the x coordinates of point P is varying with time, it's going to be dx over dt. Since I don't see any time here, I should use the chain rule. Dx over dt is going to be dx over dr times dr over dt plus dx over d theta times d theta over dt. Chain rule. One more time. Derivative of x with respect to r. I have r, derivative of this with respect to r would be 1 times cosine of theta. X dot of P would be dx over dt would be cosine of theta times dr over dt. How fast this r is, the length of this vector is changing with time. I label this as r dot plus dx over d theta. This function is a function of theta. Derivative of cosine with respect to theta is going to be negative sine r negative sine of theta multiplied by d theta with respect to time, or theta dot. And this is the x component of velocity of point P. Alright, the key point here was using the chain rule when the time variable doesn't show up in the x and y function. So we are going to use the chain rule to find the derivative of that with respect to the function. Now we are ready to start differentiating the velocity equation for the first mechanism, which is an offset slider crank. This angle was theta 2. This angle we define as theta 3 because we put the arrow here, put the arrow there. And this is S. And this is C. So for this offset slider crank, this is offset slider crank. We would like to do velocity analysis. When you want to do velocity analysis, first you should perform displacement analysis. What we learned to perform the displacement analysis, we can write the vector loop O to A equals to O to D plus dB vector dB plus vector VA. And we talked about the constant, variables, nouns, and unknowns. This is A, this is B, this is C, and this is S. The constant part of the mechanism is A and B, and C, the offset is constant. Variables theta 2, theta 3, and S. And nouns are constants plus theta 2, because degree of freedom is 1 of the variables should be given. We solve for theta 3 and S. So for velocity, now we are ready to do velocity analysis. Constant would be the same. A, B, C is constant for velocity. Variables. Whatever are the variables on displacement analysis, their derivative with respect to time would be variables here. So theta 2 is variable here. Derivative of theta 2 with respect to time, which is theta dot 2 or omega 2, is variable. Whatever is theta 3, the theta 3 is the variable here, derivative of that is variable on velocity. And S is the location or position of the slider. ds over dt, or s dot, which is going to be velocity of the slider, is going to be the variable in velocity analysis. So theta 2, theta 3, s, just put a dot on top of each, we will get the variables for velocity. Nouns are constant plus theta 2 is noun. Put a dot on the top of this. Theta dot 2 should be given. You should know what would be the velocity of input link. Whatever is the input link here, the input variable here, its derivative should be known over there. Also, we know theta 3 and s from displacement analysis. So we perform this. So we know these two. Theta 2 was given here, and theta dot 2 should be given. So we are solving for theta dot 2, theta dot is given. We are solving for theta dot 3 and s dot. For any mechanism that you will be given and you will be asked to do velocity analysis, you should do the same thing. First, perform displacement analysis, find the unknowns, and for velocity analysis, the unknowns and displacement analysis would be known, and derivative of variables would be variables, and derivative of unknowns would be the new unknowns on velocity analysis. Any questions so far? Does it make sense? Now we are ready to derive the velocity equation. We start with vector loop equation. I'm writing the x component and y component of vector loop. It's going to be O2 A cosine of theta 2 equals to x component of O2D, which is S, plus vector vector dB doesn't have any x component, or we can write dB cosine of 90 plus plus b cosine of theta 2. It's going to be S plus b cosine of theta 2. The y component is a sine of theta 2 equals to, this doesn't have any y component. This angle is 90 degree, positive 90 degree, or you can simply say that the y component is equals to c sine of 90 plus b sine of theta 2. So this is what we derived on displacement analysis. So for velocity analysis, I'm going to differentiate both sides with respect to time. Derivative of a cosine of theta 2 with respect to time should be equals to derivative of s plus b cosine of theta 3 with respect to time. So try this. Differentiate both sides, and I will ask a couple of you to come to the board and write the velocity equation. So differentiate both sides of displacement analysis just for the x component. I have the term. And find the equation for the x component. When it's needed, use the chain rule. I talked about chain rule first because we are going to use it a lot in this course. If any term is constant, we don't differentiate that, it's coming out of the derivative. You know that. Number 19. Yes. What do you think about left side? Yeah, you can come to the book. Just write the first left side of the equation. Yes. So he is differentiating the first term, which is A. A is constant, so we don't need to have A dot, because A is the length of the link. The size of the link is not changing. So this term, the term is right, but we know that it's going to be 0. So I can get rid of this. Derivative of cosine of, I'm looking for derivative of cosine of theta 2 with respect to time. Theta 2 is different than time. I should use the chain rule. Derivative of cosine of theta 2 with respect to theta 2 multiplied by derivative of theta 2 with respect to time. So derivative of cosine is negative sine. Derivative of theta 2 with respect to time is the angular velocity of theta 2, which is theta dot 2. And this A is gonna show up here. Negative A.
So for each constant that you have, like the A dot or B dot,
It's gonna be 0.
It's 0?
Yes.
Each one? Oh, because the constant is
Yes,
0.
they are not varying with time. So this is the left side. Right side, S. S is the location of the slider, it's varying with time, I'm gonna have S dot, or how fast S is varying with time. Derivative of this term with respect to time. B is not changing with time, I'll leave it there. I differentiate derivative of, I do the derivative of cosine of theta 3 with respect to time. Like same as theta 2, just change theta 2 to theta 3, you will get negative sine of theta 3 times theta dot 3, same as here. So if I rewrite the equation again, negative a sine of theta 2, theta dot 2 equals to S dot negative b sine of theta 3, theta dot 3. Equation 1. This is the equation 1 for velocity analysis. Question on this. This is important, you know how to differentiate the velocity equation from displacement equation. Everybody following me? Alright, second equation. Second equation is this guy. I'm gonna differentiate, instead of having a cosine of theta 2, I'm gonna differentiate a sine of theta 2. The a is constant. Derivative of cosine is gonna change to derivative of sine. Derivative of sine is gonna be cosine. So it's gonna be cosine of theta 2, theta dot 2 equals to C. C is not varying with time because it's the offset. Offset is constant. It's going to be 0 plus derivative of this term with respect to time, same as this guy, except we are going to have cosine, sine instead of cosine. So I'm going to get C cosine of theta 3, theta dot 3. Any question on this? See, we have started from loop closure equation, and we have here, instead of S, we have D over there. So we differentiate that. We end up to this equation and this one. This is representing the first equation, negative a theta dot 2 sine of theta 2 equals to d dot or s dot minus b sine of theta 3, theta dot 3. And second one is this guy. The unknowns are theta dot 3 and s dot. We have two equations, two unknowns. We can solve for that. Yes.
Shouldn't that the last term on the last equation be b cosine of theta 3? Like the last
Yes,
one?
thank you. It should be b. Yeah, we have right. Okay. So now it's coming to solve this system of equation. You need to use the MATLAB or your calculator to solve the system of equation, not only for this mechanism, for the future mechanism we are going to use that. As you see, we have linear equation, s dot, theta dot, and there is no s dot on this equation. So you need to change this matrix, this system of equation to the matrix form, and then you can solve it by MATLAB. How can we do that? What you need to do, you need to keep every term which is unknown, which is variable, in one side, and move the other terms to the other side. And the first equation, we already have this. S dot and theta dot 3 is in one side. The other one, which is constant, is on another side. So S dot minus, or D dot, what you know, B sine of theta 3, theta dot 3 equals to negative 8 sine of theta 2, theta dot 2. This term is noun, theta 2 is noun, theta dot 2 is noun. And S dot and theta dot 3 is only unknown. Same things here. The only term which is unknown here, B cosine of theta 3, theta dot 3 equals to A cosine of theta 2, theta dot 2. After you do that, make 3 matrix. We have 2 equations, so the size of the first matrix should be 2 by 2. 2 representing the number of equations, the second 2 is representing the variables. Second matrix should be 2 by 1, always it should be n by 1. 2 is representing the number of equations, and we have 1 column, and here also we are going to have 2 by 1. Now I'm going to fill out the terms in this 3 matrix. So the first row representing the first equation. First row representing the first equation. Second row representing the second equation. The variables are S dot and theta dot 3. The unknowns are S dot and theta dot 3. Just write them S dot here, theta dot 3 here. You can write theta dot 3 first and then S dot here, but it doesn't matter how you write them. So S dot and theta dot 3 goes there. This is the S dot. Right here, look at the first equation because this row is for the first equation. What is the coefficient of S dot in this equation? Coefficient of S dot is 1. Just have 1. And this slot here, first equation, second variable or second unknown has the value of negative b sine of theta 3. Negative b sine of theta 3. First one representing the coefficient of first variable, second one representing the coefficient of second variable. Right hand side representing the constant part. A sine of theta 2, theta dot. Second equation. First term representing the coefficient of S dot. On the left side, I don't have any S dot. So, meaning the coefficient must be 0. And the coefficient of theta dot 3 is B cosine of theta 3. And right hand side is going to be the constant part, which is A cosine of theta 2, theta dot. Now, I could write the system equation in the matrix form. Why do we need to write in the matrix form? Because your calculator and the MATLAB can solve the system equation in the matrix form. A is, all terms in A are noun. 1, B is the length of the link, theta 3 is coming from displacement analysis. D and theta 3 are noun. Right hand side, everything is noun. A theta dot 2, theta 2. A theta dot 2 and theta 2 are noun. We are solving for D dot and theta dot 2. For example, if the first one is -1, negative 4, 0, 3, d dot theta dot 3 equals to, run right hand side equals to 6 and -6 and 8. I'm just showing some numbers. We are solving for d dot and theta dot 3. In MATLAB, you need to define a matrix of A as a coefficient. Enter 1, -4, 0, 3. Define matrix B. Matrix B as -6 and 8, and then on MATLAB use A backslash B. It's gonna give you the answer of system of expression. So if I want to use the MATLAB, I define matrix A equals to 1 minus 4, just bracket 1 space -4, semicolon, and second row is 0 and 3. So matrix A, 1 minus 4, 0 and 3. Vector B is gonna be bracket -6 and 8. Thank you. -6 semicolon. Semicolon meaning it goes to the second row. And 8. And then A backslash B. A backslash B is going to give me 4.6 and 2.6. Meaning D dot is 4.6 and theta dot 3 is 2.6. If your unit is in inch, the d dot is going to be inch per second, and theta dot, since it's positive, it's going to be, the unit is radian per second, it's counterclockwise. So link 3 is moving counterclockwise for this set of number. If you got negative, meaning the theta dot 3 is clockwise, link 3 is moving along the clockwise direction. For the new homework, which is due 2 weeks from now, you need to write to solve this velocity analysis problem by using the MATLAB. What else? Yes, it is the unit that we are using for the angular velocity. Whatever is the unit for the length, A, B, and C, that unit is coming here. It is meter per second. Question? Any question on this? It's required that I should post the midterm grades. It's going to be based on the homework, so it doesn't affect your final grades. So I'm just, I have to enter something on the banner. So if you see something, it's based on your homework. So it's not, it doesn't show. Good? All right. Have a good break.